Have you ever wondered how the electricity that powers up the lights and charges your phone is generated? Today we are going to learn about the underlying concept that lights up the entire world, electromagnetic induction. Let's begin by understanding what is the magnetic field. Magnetic field is the area around a magnet in which there is a magnetic force, a force that attracts or repels magnetic objects. Have a look at this figure. Crowded magnetic lines indicate a strong magnetic force in that area. Spread out magnetic lines indicate a weak magnetic force in the area. The direction of the magnetic field is always from north to south. Let's start by making a solenoid. A solenoid is a cylindrical coil that acts as a magnet when current passes through it. Here we are using a PVC pipe and copper coil to make the solenoid. Wrap the colored paper around the PVC pipe. Once done, wrap the copper coil around it. Connect the ends to Evive's graph pin to close the circuit. Next, select the mini oscilloscope from the menu. You will notice that the graph is flat. Now take a magnet and pass it through the solenoid. You will notice a peak on the TFT screen in a positive direction. Now try dropping the magnet so that the south pole enters the solenoid first. You will notice that this time the graph is reversed. Now hold the magnet stationary. You will observe that no peaks are generated. This indicates that the current is generated in the coil when the magnet moves through it. The relative motion between the coil and the magnet induces a voltage across the coil, called the electromotive force, which in turn generates the current. The process of inducing an EMF in a closed circuit is called electromagnetic induction. This gives us Faraday's first law. Now let's have a look at Faraday's second law of electromagnetic induction. According to it, the electromotive force generated in the circuit changes with the change in flux linkage. Let's have a look at the factors that cause the change. First, the speed of the magnet. We have placed the coil in the center of the pipe, thus increasing its distance from the top. In this case, the speed of the magnet is more when it reaches the coil as compared to when the coil is at the top. You will notice the following changes. Here we have solenoids of 100 turns, 400 turns and 800 turns respectively. You can compare the graph generated by the different solenoids. Thank you for watching. If you liked this video, go ahead and give it a thumbs up. For more of such engaging videos, don't forget to subscribe to our channel.